So far in our work with kinematics, we've considered motion in one dimension. Let's look at some examples of that. We might have had a car moving in a horizontal plane, so that car would have been moving along the x-axis. We might have had a stone being dropped out of a window. That stone would move along the y-axis. What we're now going to look at is motion in two dimensions. So we're going from either the x-axis or the y-axis to both. To begin with, we're going to start with some of the basic notation we use, and then we're going to go on and answer some questions in terms of the position of a particle. So let's start off. Let's start off now with what we call I and J notation. I and J are unit vectors. Unit means they have a magnitude or length of 1. I is in the x direction, or we can say due east. J is in the y direction, or we can say due north. So let's go ahead and just put on the coordinate axis. If we put the coordinate axis on here, I'm going to look at some position vectors. Position vectors are given relative to a fixed origin, or if you like, some point. So if I put this on, this is the origin, this is going to be the x-axis, and this is going to be the y-axis. If I plot a point just here, let's say I do that one, we can see that this is 4, 2. Using I and J notation and taking meters to be the units, we can say this is 4I plus 2J meters. So I've used meters, it might be kilometers, but generally speaking we use meters. So this is using the I and J notation to show the position of this particle relative to the fixed origin. We could write this in column form, and that would be 4, 2. So 4, 2 meters. Let's look at this point right here. This point is going to be on the y-axis, so we have 0I and we've got 5J. So we'd simply write this as 5J meters, or in column form we would have 0, 5. If I chose one over here now, let's pick this one just here. This is on the negative x-axis, so we could say this is negative 4I meters, or if we wanted as a column vector, negative 4, 0 meters. Let's put another one down here. Let's have this one, and this is going to be now negative 3, so negative 3I. Then we're going to have now minus 3J meters, and as a column vector we could write this as negative 3, negative 3. So all we're doing is looking at the position of the particle relative to a fixed origin using I and J notation. We're going to work through a few basic questions before moving on to some more challenging topics in later videos. So in this question it says a golf ball is hit so that its position in meters at time t seconds is given by r is equal to 30 ti plus 25t minus 4t squared j, where I and j are horizontal and vertical unit vectors respectively. Let's take a moment to break this down. R is simply the position. So if I wanted to say now R, for this particular one, it's 4I plus 2J meters. That is the position. R is given as the position relative to some fixed point. What we have here is 30 Ti. When we have now the X and Y coordinates, these are both functions of time. They're independent of one another. They're governed by the time. So this is one function of time. So if I wanted to write this now, and another way you might want to look at it, if I just write this up, I could write this now as the x coordinate. So if you like, x is given as 30t, and the y coordinate is given as 25t minus 4.9t squared. So all this is saying is after no seconds, the x coordinate will be 0. After 1 second it will be 30, 2 seconds, 60, and so on and so forth. For y coordinate, we're simply subbing these in. So these are two different functions of time. This one right here is going to give me now the y coordinate, or if you like, j meters. I and j are horizontal and vertical unit vectors respectively. We've looked at that, and that's what I introduced before. If you want to get some idea of what this looks like, we could have now these two perpendicular vectors which would look like this. So all we're saying now is the following. We're simply putting on here that this is going to be j and this is going to be I. So we can say now that this is 1i meters and this is 1j meters. That's all they are. They're just now small 1 unit vectors. So it says in part 8, find the position of the ball when t is equal to 0, 1, 2, 3, 4, 5 and 6 seconds. In B we need to plot the path of the ball. And in C it says from your plot estimate the horizontal distance travelled by the ball when it hits the ground. In later videos we're going to look at work with projectiles, but for now I'm just going to go ahead and work with this in basic form. So let's just extend that down and we'll put this that way. Okay, so let's put that there. So what I'm going to do at this stage is just build up a table of values. This is the general method that we use. So what we'll have is a table of values. We will have now the time t, then we'll have the x and the y coordinates. So we could call these, if you like, parametric equations with the parameter being t. So let's put in our values of t. We'll look at xi meters and yj meters. So we're going to have 0, we will have 1, 2, 3, 4, 5 and 6. So let's start off now with the x coordinates. If t is equal to 0, 30 times by 0 is 0. If t is 1, 30 times by 1 is 30, 60, then we're going to have 90, 120, 150, 180. So we can see that this is a linear function. It's going up by that fixed amount, and we could graph this with a straight line. Remember though, that's only giving me the x coordinate. What we now need to do is find the y coordinate. So all I'm going to do is substitute in here t is equal to 0, 1, 2, 3, right the way up to 6. So quite clearly if we put 0 in, we're going to get 0. Before I go any further, what I'm going to do is just sketch up what this is going to look like. If this golf ball is hit from a horizontal ground and it's got, so it's not done from above, what we're going to have is something like that. So we'll have now a curve. So what we've got here is t is equal to 0, the time is equal to 0, and we can say that the x coordinate's 0 and the y coordinate's 0. It's on the floor at what we would call the origin. We're going to come round and then we're going to hit the floor over here, and we can find a value of t for that. So this is going to be the flight path, or if you like, the trajectory. So let's go ahead and now start subbing in. So what I'm going to do is set this up on the calculator. I'm just going to plug this 25, so what I'm going to have is 25, then I'm going to alter these values, 25, then we'll have minus 4.9, and then we're going to have the 1 square. As soon as we see now a quadratic function, we can tell that this is going to be a curve. So that's going to give me 20.1, so I can put that in. So just here, we've got 20.1. So if I wanted at this stage, I could say that I've got 0i plus 0j meters. I've got now 30i and then plus 20.1j meters. These now are the positions. So find the position of the ball. That's how I should write it in my final answer. I'm just going to go ahead and write them in the table and then we're going to plot them. But if you're asked, these are now the positions. So all I'm going to do is switch this over. So if we now put in t is equal to 2, so t is equal to 2, and then that's going to give us now 30.4. So let's put on here 30.4. Then we'll put in 3, so let's do 3. So if we do that, putting in 3. So let's go ahead with 3. That's going to give me now, what have we done wrong? Oh, we need to put in a 3, don't we? Missed out a 3, there we go, 30.9. So 30.9. So you can see at this stage now we are gaining less and less. So the positive velocity is reducing now in the y direction. So let's switch this over. Let's now put in here 4. So we'll put 4 in. So 4 is going to go in here and plug it in 4. So that gives us now 21.6. So 21.6. A sketch and a plot are different. Plotting means that we need to find the points. If you're just asked to sketch this would be perfectly fine. And when you come on to projectiles, you will do that. The topic here, though, isn't about projectiles necessarily. It's just about plotting the points of these particles given some time. So 2.5, so let's put that on. And then if we do 6, this is going to be interesting. So let's do 6. So what we've got that when we put 6 in, this is going to end up giving us a negative value. And that's perfectly fine if we've got now the negative value, so negative 26.4. Okay, so if we look at our model, what this is essentially saying is after 6 seconds, it's going to be somewhere down here. Remember, this is where now the y, or if you like the j component, y is equal to 0 at this point. So what we've got is actually gone through the floor. Now this would make sense if you looked at it in 2 different ways. One particular way is if we hit the golf ball off a ledge and it could still go below, so we had a negative displacement, that would be perfectly fine, because we could see, for example, let's say that that's going to be, let's say that's 100 meters, then that works out perfectly fine. Alternatively, what we could say is that this hits the floor. If it's hit from a flat level and lands at the same level, then we are going to simply say that it takes less than 6 seconds to hit the floor. Right, so let's go ahead. So you would write these out as, say, 30i plus 20.1j, 60i plus 30.4j meters. I'm not going to write them all out as I'm running out of space. So let's go ahead and plot this. We'll plot this, I'll put it on here. So what we're going to have is the following. And let's look at a scale. We need to go up to 180 and then from negative 26.4 to about 31. So let's have a go at that and we'll see how well this goes. So if I now plot along the x-axis, let's put these on. We will go for this point right here. We will say that's 20, 40, 60, 80, 100. So let's put 100 there. Then we'll go 120, 140, 160, 180, and we'll have 200 there. So that is going to give me the x-coordinate. We know this is the x-axis, or xi meters. And then we'll have yj meters. So if I put this on, what scale can we use? I don't think I'm going to squeeze too much on here. So I'm going to say that that's going to be 10. We will say that that is going to be 20. We will say that that is going to be 30. I suppose I could have doubled that up, but this should hopefully give you some idea. Negative 10, then we've got negative 20, and we've got negative 30. In an exam, generally you'll be given the scale to work from, or at least something that, I mean, I'd like some more room up here. I could probably squeeze it on here, but we'll leave it as it is for now. So let's go ahead and plot this. So we know that it's going to start at 0, 0, so we can put that just there. So 30, then we're going to have 20.1. So 30 is going to be here, 20.1 is going to be just there. Okay, so that's what we've got. So we're going to be coming up with this curve. Then if we look at the next one, we've got 60. So 60 is this one just here, and that gives us 30.4. So 30.4 at 60, which is going to be about there. Then we got 90, and that's going to be 30.9. So we can see at this stage now with about there. Then we got 120, which is here, and 21.6. So we're on the way down, and that's going to be about there. Then we got 150, 2.5. So at this stage, we're nearly hitting the floor. 150, 2.5. Let's put that just here. There's 150, and that's about 2.5. And then if we look at the next one, we got 180. So 180 is going to be here, and we've got negative 26.4. So assuming that this was hit, and that's going to be about that. Assuming it was hit in this particular model, then what we've done is gone through the ground. If it was hit with this one, we could say now that it's just lower than when it started. So let's now draw this. This is going to be a nice sweeping curve through the points. Yours will be better than mine as I'm on the tablet, which is making it a little tough. Let's just straighten that out. For some reason it's gone, or curve it out I should say, rather than I think I was going off the end of my tablet. So we're going to come around with the curve like so. We're going to come through these points, through this point here, and then we're going to come down. We're going to meet the x-axis or the floor somewhere around there. That's a rough shot. And then we're going to come down to here, and we're going to get that point just there. Okay, so that's what we have. So there we go. That's our plot. Okay, so from our plot, we need to estimate the horizontal distance travelled by the ball when it hits the ground. Well, that's going to be this point right here. So if we look 120, 140, 150, we could probably say 154, 155 metres. Remember, that purely is an estimate based on our plot. In the video on projectiles, you'll find that exact value if you're given projectiles. So let's say this is going to be about 100 and let's just say 155 metres. What we could do if we really wanted is find out the exact distance. If we consider now that this would be equal to 0, just consider now that y would be equal to 0. So y would be equal to 0. We can factor out t, and that gives me 25 minus 4.9 t. So t is equal to 0, which gives us the origin just there, or 25 minus 4.9 t is equal to 0. So we could say now that t is going to be equal to 25 divided by 4.9. Of course, all we would need to do with this now is plug it in to x. So x gives us 30t, so we can say that the x coordinate, or if you like the the position in terms of I, is going to be 30, and then we're going to have 25 over 4.9. We weren't asked to do this, we were asked to do it from the sketch. But if we wanted to find the exact distance, or if you like the range, we would call it the range, we could say that's 25 over 4.9, and that will give us the value. So what's that give me? 153. So 153.06. So that would be just there. So 153.06 metres. And we have that. I suppose you'd be given a level of accuracy to round that to. Let's see what we've got. I've just done it to now the nearest centimetre. So that's what we would have. We've just done it from the sketch, and of course my sketch is highly inaccurate because I've chosen such a poor scale. So there we go. That's plotting the path of this ball. So we're looking at the position now relative to the time. These are both functions of time. Okay, two children, A and B, run so that their position vectors in metres at time t seconds is given by RA is equal to TI plus TJ, and RB is given as 4 plus 4t minus t squared I plus TJ, where I and j are unit vectors directed east and north respectively. We're asked to plot the paths of the two children from 0 to 4 for the time, and we're asked what happens when the time is equal to 4. If we look at this, this is simply a linear function. This is the line y is equal to x, and if we wanted to do that, we could do. This one is not. This is going to give us now a quadratic function in t, so we're going to get a curve. So child A is going to be on a nice straight line. This child is going to be on a curve. So let's go ahead and just draw these up. So this should be relatively straightforward. So if we do now the following, and we can put them both in the same one, it's entirely up to us. I'm just going to do two different ones. So what we'll have then, let's put that on. We want an x and a y, or an I and j, and we're going to substitute these in. So let's do that. Let's put this on. That will do like so. So we'll have now some value of t. So let's put in t here, and then we'll have xi metres and yj metres. So if we look 0, 1, 2, 3 and 4. If we just think we're subbing this in, so 0, we're going to have 0, 0. We're going to have 1, 1, 2, 2, 3, 3, and then 4, 4. So this is going to follow a linear path, and that linear path is y is equal to x. So this now is the position of child A at time t seconds in metres. If we look at the next one, slightly more challenging to calculate, as we've got now some quadratic function in t. So if we put this up, let's put that on here, let's put this in. We've got now the following. We've got t again to be 0, 1, 2, 3, 4, and x and y. So as stated, I could have done this on in the same table. We're certainly going to plot them on the same coordinate axis. So we're going to have now on here, if we substitute in 0 for the x coordinate or the I component, 4 plus 0 is going to give me 4. If we sub in 0 for the y component, that's just going to give me 0. Okay, I can of course go ahead and just set this up, or I can do it in my head. I'm going to just set it up on the calculator for the x coordinates. So what we got is 4, then we got plus 4 lots of the number, and I'm going to put in 1, then minus the number squared. So I can use this each time. I suppose with these numbers it should be relatively straightforward to work. So that's going to be 7, and then what we're going to have is 1. So we could just go ahead and fill these out. 2, 3, 4, and we're going to have 5. That's just for the j component. We know that that is linear. So let's just go ahead and find our x1. So subbing this in, we'll put in 2. So if you want to do it on paper or in your head, do it in your head. That's going to give me 8. That's 8. Then on the next one, let's put in 3. So if we put in 3, we're going to end up now on here with 3. That's going to give me 7. So 7. Then this now is going to be symmetric. I'm just going to put them in just to show that. If we put in 4, hopefully you see what we're going to end up getting. On this we should now get 4. So let's put in on here. So put that in as 4. There we go. And that will give us that one. And then finally we need 5. So let's put in 5. So 5. And then we're going to have that one. And that is going to give us -1. So we can go ahead and plot these. So we're going on the x-axis now. If we look at the x-axis, we're going from -1. So -1, and then we're going to go up to now 8. And on the y-axis, we're going to go from 0 to 5. So a bit easier to work with this time. Let's go from there. We'll have something that looks like, let's change that over. And we'll have something that looks like this. So if I put this on, that's what we're going to have, and something that looks a bit like that. So on the bottom, let's go ahead and we will do now. So we're going to have -1, we will do 1, we will do 2, we'll have 3, we'll have 4, 5, 6, 7, and we'll have 8. Okay, on the y-axis, we're going to have now 1, we'll have 2, 3, 4, and 5. So if we look now at plotting the path of child A, this is simply a linear function, and we're going to get the points 0, 0, we're going to get now, so 0, 0, 1, 1, we're going to get 2, 2, 3, 3, we're going to have 4, 4, and that's it. So we can go ahead and plot now that path. We don't extend it any further. That is what we end up having. So that now is RA. So this is the position of child A after t seconds given in meters. So let's just put this on. That is the position there. If we look at the next one now, we need to start off. We're going to have here 4, 0. So if I just plot these points, so 4, 0 is going to be here. If we wanted to write this as I and J notation, we could write this simply as 4i. Then we're going to have 7, 1. 7, 1 is going to be here. We're going to see a sweeping curve now. Then we're going to have 8, 2. 8, 2 is going to be just here. We're going to have 7, 3, and this is where it becomes symmetric. We're going to have 4, 4, and that is going to be just here. And then we're going to have now -1, 5, which is going to be just here. So that's what we get. So if I wanted to draw this curve, the curve now for the second child would look something like this. So we'll come through, we'll come round, and it'll look give or take. I mean, this isn't brilliant, but it gives us some idea. So this now is the position. So what we've got is the following. So the position will look something like that. So there we go. That should be a little neater, but that should be a sweeping curve. So what happens when t is equal to 4? Well, they run into each other as they're in exactly the same position. Remember, this is a position relative to fixed origin, and essentially they're going to be in the same place. At t is equal to 4, we can see from here, if I just highlight this, at t is equal to 4, the x and y coordinate 4a is going to be 4, 4, and we have exactly the same. So we can say that they're in the same position. You might get a nasty question on an exam asking you about who had the fastest velocity, average velocity, and the fastest average speed. If we consider now, if that question does come up, let's just change this back over. If we look at the path now that this one has followed, we've got now on here that its velocity, the average velocity, will be the same, because what they're at this point after 4, when t is equal to 4, they're both at 4, 4. But if we look at the speed, we can see that this one has travelled a lot further. So if you're ever asked that question, we can say that the velocities are the same, as they're in the same place at the same time, but due to the curvature of this particular child has run a lot further, so they would have a higher average speed. So quite a nice question, and that one is just completed with a table of values. So it's not a sketch, it's a plot, and we put them in. So that's a brief introduction to kinematics in 2 dimensions, and we've simply looked at the position of a particle given a time. We've had some linear functions, and we've had some quadratic functions which give rise to a curve. If you're looking for videos on projectiles, do check out the site, as this is simply now looking at plotting given particular functions where both x and y are defined as functions of t.